Time flies like an arrow. Fruit flies like a banana. Tell me, in each sentence, is the word flies a noun or a verb? Take a beat. First sentence, verb. Time is doing the flying. Second sentence, noun. The fruit flies. They like the banana. Two sentences, same word, different job. And a tagger has to get both right without knowing what banana means. Video 3 of Lecture 7. Part of speech tagging. The classic first task in every NLP textbook. 97% solved for English, sometimes called the hello world of NLP. And yet, the last 3% is where the real linguistics lives. Today we walk the tagset, the taggers, and the ambiguity that still gets researchers out of bed in 2026. In video 2, we walk tokenization. Turned raw text into a stream of tokens. Great. But a token by itself is just a string. The parser downstream, the NER model downstream, the semantic role labeler downstream. They all want to know what kind of word each one is. Noun, verb, adjective, determiner. That is the job of the POS tagger. Second station on the belt. Today's puzzle. If POS tagging is 97% solved, why does every NLP course still spend a whole lecture on it? Answer. Because the 3% that isn't solved is where every hard problem in language lives. Ambiguity, context, words that change job depending on the sentence around them. Get POS right and everything downstream gets easier. Get it wrong and everything downstream falls apart. Today's 3 beats. First, the Penn Treebank tagset. Marcinkiewicz, Santorini, 1993. 45 tags that quietly run NLP. Second, how you actually build a tagger. From HMMs to neural taggers. 3 generations, same task. Third, the ambiguity that keeps this task honest. Flies, leaves, saw. Why context is everything. Beat 1. The Penn Treebank tagset. Marcinkiewicz and Santorini published it in 1993 at Penn. 45 tags for English. NN for common noun. NNS for plural common noun. NNP for proper noun. VB for verb base form. VBD for past tense. VBG for gerund, VBN for past participle, JJ for adjective, RB for adverb, DT for determiner, IN for preposition, and on. 45 in total. Every English NLP paper since then has cited it. Why 45 and not 5? Or 500? This is the interesting part. A coarser tag set, like universal dependencies with 17 tags, loses information. Was that verb past tense or present? A finer tag set, with 100 distinctions, is impossible to annotate consistently. Even trained linguists disagree at that resolution. 45 is the number the field settled on because it's the number you can actually train humans and machines to agree on. Beat 2. The first generation of taggers. 1980s. Ken Church at Bell Labs. Stochastic part-of-speech tagging using a hidden Markov model. The idea, every token has a hidden tag, and tags follow patterns. Determiner is usually followed by noun. Modal is usually followed by verb. Learn the transition probabilities from a tagged corpus. Then viterbi your way through a new sentence to find the most likely tag sequence. HMM taggers hit 96% on English by 1990. Second generation. 1995. Eric Brill's transformation-based tagger. Different approach. Start every word with its most frequent tag. Then learn rules that fix common mistakes. If a word is tagged as noun but the previous word isn't to, change it to verb. Rules that a human can read. Elegant. Not the best accuracy, but the most interpretable tagger ever built, and still cited whenever people talk about explainable NLP. Third generation. Neural taggers. Bidirectional LSTMs from around 2015. Then transformers. Bohnet and colleagues 2018 hit 97.96% on the Penn Treebank test set, which is basically at the ceiling of human inter-annotator agreement, meaning the machine is now as good as the humans who made the ground truth. Progress got hard because the truth itself became fuzzy. Beat 3. The 3% that isn't solved. Ambiguity. Take flies. As a plural noun. fruit flies, house flies. As a third-person present verb, time flies, she flies planes. A tagger cannot decide in isolation. It has to look at context, which is exactly what neural models are good at. But when the context itself is ambiguous, that is where the last errors hide. More examples. Leaves. Noun. The leaves are falling. Verb. She leaves at 5. Saw. Noun. The saw is on the workbench. Verb. I saw the movie. Book. Noun. A great book. Verb. Book the flight. Every one of these is a word where you cannot tag without reading at least 2 neighbors. And in some sentences, 3 or 4. The nastiest kind, garden path sentences, the old man the boat. First reading, the old man is a noun phrase, then you hit in the boat and the parse falls apart. Actual reading, the old is a noun phrase, man is a verb meaning to staff. The old people are staffing the boat. Every tagger gets this wrong on the first pass, because the frequent tag for man is noun. Practical picks. If you need POS tags in production, use Spacey or Stanza. Both ship with pre-trained neural taggers hitting 97+. If you need to understand why a tagger got something wrong, read Brill 1995 and squint at the rules. If you're pushing accuracy past the ceiling, you're actually doing linguistic annotation research, not engineering, and you should be reading J&M Chapter 8 cover to cover. 3 takeaways before the quiz. 1. Every POS tagger for English uses the Penn Treebank tagset, 45 tags. Marcinkiewicz, Santorini, 1993. It's the Goldilocks resolution, coarse enough to annotate, fine enough to be useful. 2. 3 generations of taggers, HMMs, Church, rule-based, Brill, neural, Bohnet, and successors. Each one moved accuracy from the low 90s into the high 90s. 3. The remaining errors are ambiguous words like flies, leaves, saw, book. They need context. Garden path sentences are the worst case. This is the 3% that still keeps researchers busy. Quiz 1. Why did the field settle on the 45-tag Penn Treebank tagset instead of something coarser or finer? A. It was chosen at random. B. 45 tags hit the sweet spot where humans and machines can both agree on labels while still preserving useful distinctions like tense. C. It matches the number of keys on a keyboard. Or D. Marcus wanted it to be prime. B. Coarser tagsets lose the tense and number distinctions downstream tools want. Finer tagsets push annotators into disagreement with each other. 45 is where trained humans agree with each other, and where machines can be trained to match them. Quiz 2. In the sentence "time flies like an arrow," what tag does flies get? A. NNS plural noun. B. VBZ, third person singular present verb. C. JJ adjective. Or D. RB adverb. B. VBZ, time is doing the flying. Compare with fruit flies like a banana, where flies is NNS. Same word, different job, decided entirely by the 2 neighbors. Quiz 3. Modern neural POS taggers hit around 98% accuracy on English. Why doesn't the field keep pushing that number up? A neural nets have a hard cap at 98% by design. B. 98% is already at human inter-annotator agreement. The remaining errors are cases where humans disagree with each other, so the truth itself is fuzzy. C. The Penn Treebank corpus is missing. Or D. GPUs, cap out. B. Bohnet et al. 2018 hit 97.96%, right at the ceiling. When the machine matches the humans who made the ground truth, further gains require redefining the truth. That's a linguistics problem, not an engineering one. Back to the puzzle. POS tagging is the hello world of NLP 97 solved. 3% that is actually hard. Station 2 on the belt. Once you know each word's job, the next station wants to know how the words fit together. What modifies what? What is the subject? What is the object? That is parsing. Video 4. Next time, parsing, finding the sentence's skeleton, constituency trees, dependency arcs, and the classic garden path example that has been breaking parsers for 40 years, the old man the boat. Hit subscribe.